Hello, ladies. You're going to need these two PowerPoints. The second one we started last class, and we're going to finish that one. And then the third one on Coulomb's law. We're going to start this one and finish it when I come back and see you in class. So grab these two.
So let me do this. I want to show you something, and I want to see if you can perhaps figure out why what's happening is happening. But in order to do that, I got to pin my screen so I can see that you can see it. Okay. So I want to show you something. And now, first off, go to the slide, go to the PowerPoint that we didn't finish yesterday. It was the one that had the triboelectric sequence chart on there. Remember the chart that we used to figure out if we're going to rub two materials together, which one will be positive and which one will be negative. Find that chart, because you're going to need that to be able to answer the questions about what I'm going to show you here. Okay. All right. So here I've got a rubber balloon. So find rubber. Here's a rubber balloon, and I'm going to go ahead and rub it on this cotton sweater. Really annoying. Okay. I'm just going to set this down right there. Okay. Now, here I've got a glass rod. I have two materials I'm going to rub this glass rod with. Okay. The first material is going to be flannel, which is also known as wool. So I have a glass rod and wool. All right, here we go. So I'm going to rub this. Okay. Now, you should know what charge this is. Okay. Now I'm going to take the balloon. You should know what charge is on the balloon. So right now in your head, you should know what's going to happen when I bring this near the balloon. So I'm going to take the balloon and I'm going to hold it so it can move. Here we go. I'm going to bring this glass rod. Now think about what you expect to see happen. Here we go. Did you expect that? All right, look at it again. As I bring it closer, obviously it's attracted to the balloon. Okay. Hopefully you all expected that by reading the chart. Now I'm going to show you this. I'm going to take the balloon, I'll set it down again. I'm not going to change anything to the balloon. But now I'm going to rub this glass rod with rabbit fur. Okay, here we go. So this is rabbit fur. Okay. I'm going to take it now. I'm going to take the balloon again. And now I'm going to bring the glass rod near the balloon. Here we go. Do you expect that? Do it again. Let me hold on. Let me do this one more time. Let me get more charge on here. Put that there. Let me do this one more time. Let's see if we can get it. Okay, here we go. There we go. See that? Did you expect that? Okay, so now let's talk about this. Let me unpin the screen. Okay, how many of you saw what you expected to see? Put your hands up. Okay, who wants to explain what charge is on the balloon? Come on, man. What charge is on the balloon? Remember, this is rubber. This is cotton.
Negative.
What's that?
Negative charge.
Okay. How do you know that, Maddie?
Because rubber is lower down on the chart than cotton.
Okay. And so we know the substance above is going to be positive. Okay, so this is negative. Do we all understand that? All right, so this stays negative for both demos. That doesn't change. All right, so when I took the glass and the flannel, which is wool, all right, What charge is the glass rod going to have when I rub it with the flannel? Somebody else besides Maddie.
Positive.
Huh?
Positive.
Okay, and how do you know that, Chelsea?
Because of the chart, it's like higher up. It's like the third one. On
The
line.
glass is.
Yeah.
Okay, so if this is positive and this is negative, did it make sense then why they went together?
Yes.
Okay, all right. Now, what happened when I rubbed it with the rabbit fur? What charge is the glass rod? Somebody else. When I rubbed it with the rabbit fur, somebody else, what charge?
It was negative.
Who said that?
Me.
Samantha, okay. It was negative. How do you know that it's negative now?
Because the fur was above glass on the chart.
Okay, so first here, glass is down here. So glass is going to be negative. So does it make sense then why the negative balloon moved away from the negative rod? Okay, so you see how using that chart, if you know what the materials are, you can determine what thing's going to be positive, what thing's going to be negative. All right. So when I did this, this became negative. Where did the electrons come from? When I do this, where do the electrons that have come onto this, where do they come from? Well, before I do this, this is neutral. It has the same number of negatives as positive charges. But when I do this, it has more negative charges now than it had. Where do those excess negative charges come from? Well, I have one person that knows. Allie?
They came from the cotton on your shirt.
Okay. And which charges are the only ones that actually move?
The electrons.
That's it. Positive charges don't move. Only the negative charges move. So if you want to make something negative, you give it negative charges. If you want to make something positive, what do you do?
Do you take away its negative charge?
You take away the negative charge. It's only the negative charges that are you are moving from one thing to another, okay, to make something positive or negative. You're not doing anything to the positive charges because you can't. The protons cannot be moved because they're inside the nucleus, and there's a thing called the strong force you learned in chemistry that holds them together. It's almost impossible to take them out of there and move them around. But remember that slide we talked about electrons, you can easily pluck off energy levels and move them because they're very weakly held around the nucleus. Okay, so the electrons I'm probably stripping off my sweater are the ones on the outer levels of the atoms that make up my sweater. Okay, and they're just being stuck onto this. All right, good. I'm glad you guys figured that out. So here's what I want to show you now. So let's go to the slide if you don't already have it up, which you should. Okay. So we left off with this chart here. Okay, so we've been using this chart to figure out which thing was negative and which was positive. Okay, so let's go here. Now I want you to look in this blue box. This says charged objects will either attract or repel other charged objects, depending on the relative charges. You learned that in middle school, man. That's not even a high school thing. But look at the next statement. The next statement says the amount of attraction or repulsion. So how well they come together or how well they move apart depends upon two things, guys. Depends upon the magnitude of the charges and the distance between them. So what we're talking about is the amount of charge and how far apart they are. So I want you to think about this. If these two things are going to go together, okay, that's the attraction. How well they go together depends upon the two things we just circled. How well they go together depends upon how much charge both of these items have and how far apart they are. If I hold them out here, you're probably not going to see this want to go to this rod. You don't see it until it's closer together. Okay, so the smaller the distance, the stronger the force. So that's an inverse relationship. All right. But what about the amount of charge? The greater the charge, the greater the force. Wouldn't that make sense? Okay, so that's a direct relationship. It's important to know those two relationships when we start getting to Coulomb's law. All right. So you learned in middle school what was called the law of electrostatics. Now, you never learned it as that phrase. You just learned, hey, like charges repel, unlike charges attract. That you already know. We just happen to call that the law of electrostatics. Now, here's our second way of charging an object. First way was friction. That's when you rub something on something else, you strip electrons up of it. Same thing when you're brushing your hair. That's friction. But there's another way you can charge an object. But look at the highlighted word. Induction. So we have friction and now we have induction. Induction can be used to create charges on objects, but only temporarily. Okay, induction is not as quote unquote permanent as friction. All right. So what does this mean? Well, look at what this says. This says if a balloon is rubbed with a certain material, in this case cotton, it becomes electrically charged. So this balloon becomes negative. Now, what does this temporary charge mean? Well, look, if I take this balloon, now this wall right here, ladies, is neutral to begin with. Everything is neutral to start off with. Everything. Okay. So this is neutral. That means it has the same number of negative as positive charges on the surface of it. And which of those charges move?
Negative charges.
Thank you, negative. Why is it taking you all so long to say the obvious answer? Okay, negative charges move. So if I take this balloon and it's now negative, and I bring it near the board, don't touch it, just near it. What will all the negative charges in the board do?
Go to the other side.
They'll go to the back side of the board. So what charge will the surface be?
Positive.
Positive. So you see, by bringing the balloon near the board, I am temporarily charging the side of the board, aren't I? It is temporarily. Why is it temporary?
Is it when you move the balloon, it goes back?
Yep, because when I take the balloon away, the board goes back to being neutral. So it's only going to be charged as long as the charged object is near the other one, near the neutral one. Okay? Does that make sense to everybody? All right? So that's what induction is. Induction is when you temporarily charge an object by bringing a charged object near a neutral one, near it. Okay? Now, watch this stuff. So since this is negative, and I bring it near the board surface becomes positive. That's why when I leave it on the board, it sticks to it. Okay? It sticks to it because it has temporarily charged the surface of the board to be positive because all the negative charges are on the other side. So the balloon will just stick to the board. And it'll keep like that as long as the balloon maintains its negative charge. Now, if the air in this room, and today it's not, but if the air in this room was moist, if the air was moist and it was humid, the negative charges on the balloon would somehow dissipate out into the moisture. And the balloon would lose its charge, and then the balloon would just fall. This works really well when it's a dry environment. Okay? That's why you guys have bad hair days on drier, cold winter days than you do humid ones. Okay? All right. So that's induction. Induction is when you have created temporarily a charge on an object because you bring a charged object near it. So look at the picture here. So if you look, what we're saying is all these electrons, which were all here, they were all here. They've all moved to the backside of the wall, making the surface of the wall positive. The other side of the wall is negative, and therefore the balloon is going to be stuck to the wall. Do we understand that? Do we all get that? All right, that's induction. Okay. All right, water. When you learned about water in chemistry, if you look at the molecule of water, it's kind of a weird molecule. It's askew, right? The hydrogen atoms are at an angle to the oxygen atom, which they're bonded to. So like right here, this is a molecule of water. The positive signs are the hydrogens and the negative is the oxygen. And so what you end up getting because of the way the water molecule is positioned is you get a positive side and a negative side. All right, this becomes negatively charged. This side is positively charged for this molecule here. Okay, one end is negative, one end is positive. And when you have two charged sides, we call that a polar molecule. Okay, because you have two charged sides. Now, I want to show you this. This one is interesting. So let's see if you can figure this out. So here I've got, okay, this, and I'm going to pin my screen so I can make sure you guys can see it. So again, make sure my screen is big. All right, so here I've got a burette that has colored water in it. Okay. So here's a burette with colored water, and I just got a container down here, and I'm going to turn this on. I want you to see if you can see the stream. So let me move out of the way. Tell me if you can see the stream. Everybody looking? Here we go. Can you all see the stream of water? Okay, now watch. I'm going to take this balloon. I watch the water stream. Here we go. Watch. See how I can bend the water? All right, let me do it on the other side. Here we go. Watch the stream. I can bend water. I'm not even touching it. All right. Now, the question is, why do you think that is? Who wants to try to answer that? Why is the water stream bending? Anybody? Nobody has a clue.
Since
Go ahead.
since like the water is a charged, since it's polar, then it's like attracted to the oppositely charged side.
Mm-hmm. So look here. Let's look at this. Let's say this is the stream of. Oh, no, let me go back. Okay, let's say this is the stream of water that is just a regular stream of water before I bring anything near it. So we're going to have positive and negative charges kind of interacted throughout the whole thing, right? All right, so that's like a neutral stream of water. All right, but if I bring a charged balloon, let's say it's negative, near this stream of water, what will all the electrons on this side of the stream of water do?
Move to the other side.
They're all going to go this way. So when they all move to the other side, the positive charges aren't going to do anything. But when they all move to the other side, I then end up getting a side that has nothing but positive charges on it, and the back side, which has all the negative charges plus a few positive charges that were still there. So this side becomes positive, this side becomes negative whenever there's that negative balloon near it. So now can you understand why the water bent towards it? Okay, again, that's induction. And what I'm getting at is this idea that's called polarization. And polarization is something that happens because of induction. All right, when you bring a charged object near a neutral one, you're going to charge the neutral object because the negative particles or the negative electrons are all going to move to another side, to the opposite side, if the charged object's negative, making one side of the object negative and one side positive. That's called polarization. And polarization is only temporary. As long as you have a charged object near something, that's what's going to happen. If it was a positive balloon, if I somehow manage to make the balloon positively charged, same thing's going to happen, except the negative charges will all be on this side of the water, right? And so this side, you'll have your positive charges. So this side will be negative, this side will be positive, but the water stream will still bend towards the balloon. So I have still created the same effect through polarization because of induction. All right. Another thing you can see with that is this. I don't know if you can see this, but let me pin my screen again so I know you can see it. Let's see. Okay, you see in here I've got little bits of paper, okay, inside this container. Now I'm going to take this balloon. So I don't know if you can see this, but if I take this balloon and put it in here, sometimes it works, sometimes it doesn't. Just, I've used this balloon so much, I think it's losing its here. Let me do it this way. All right, let's look at packaging peanuts. So you see here, I've got some packaging peanuts. So I put this in here, you see I can actually pick up a packaging peanut. And so this is the same thing. I am inducing a charge in that packaging peanut because of polarization. So all the negative charges in this packaging peanut have moved to the bottom of the packaging peanut, making the top of the peanut positive, which is why the peanut sticks to the balloon, okay? All right, so that's just another example of it. But what's a use for it? You know, how can we use that? What would be a good use of this idea of polarization in everyday society? So let me, come on, man. Oh, there we go. All right. Oh, I can't figure it out. All right, so there's this thing called electrostatic precipitators. And basically what it is, electrostatic precipitators are like a bunch of charged balloons that kind of are in a screen. So it looks like a screen. If you look at these precipitators, it looks like a window screen. But think of it like a lot of little tiny charged balloons. And so what they do is they put this electrostatic precipitator on the top of a smokestack. So if you've got these big factory smokestacks, all right, that billow out all this pollutant, smoke and so on, they put these electrostatic precipitators on top, and these are little tiny charged, notice I use the word charged, they're charged screens. So these screens have a charge. And so when the pollutants come up through the screen, it's like these little packaging peanuts. As they come up through the screen, they get attracted to the screen due to polarization. And they stick to the screen. And so the smoke that comes out the other end of the screen is much cleaner now because the pollutants are all sticking to the screen due to the charge of the screen. And all they do then is they take the screen out, rinse it off, and put it back into the smokestack. And it just, that's a way they can use this to clean the smoke or these pollutants that come out of these factory smokestacks. It's pretty ingenious, I think. All right. All right. So let's go here. So here's the picture we said of the charged balloon. And again, we can notice that if this is all negative, then all the positives, this side will all be positive. This side back here will be negative, but only as long as the balloon is near the water. All right. But again, this is polarization. The water is polarization. Okay. All right. I'm not going to spend time on this. You can look at that. But I want to get into Benjamin Franklin. Oh, I didn't show you this. Hold on. Before I get to Benjamin Franklin, this is kind of cool. So let me pin my screen again so I can see. Yeah. All right. So look here. Look at this. Regular cocaine, right? Okay. I'm just going to put the cocaine right here. All right. Now, this is a neutral cocaine. Nothing special about it, but it's neutrally charged. Okay. Just going to put it there. Now, I'm going to take this balloon. Now, I want you to think about what you think is going to happen. I'm going to rub this balloon on my cotton sweater, and I'm going to hold the balloon right next to the can right here. Think about what is the can going to do? I'm not going to touch the can, just going to bring it near the can. Okay, this is friction. Now I'm going to do induction. Watch what happens to the can and see if what you thought happens. You know what? Let me get a different balloon. Let me get this balloon. Here we go. I have to use the balloon for a while. I don't think it works very well. All right, here we go. All right, here we go. Oh, yeah. Is this what you figured would happen? Who can explain why this is occurring? You know, this balloon works better because it's burnt orange. Why is this happening? Who wants to take a stab at that? Anybody? Anyone? Nobody wants to take a stab at it. Maddie has her hand up, but does anybody else have her hand up? Come on. Think about the wall. Think about the wall. What's going on? Think about the wall. I mean, this is a neutral can. This is like the wall. Man, you're all looking at me like you have no clue. This is negatively charged. I bring it near the can. If this is neutral and I bring it near the can, I'm going to hold the can. But if I bring it near the can, what will the negative charges in the can do when the balloon is here?
Go to the other side.
They're all going to go to the back side. So what charge is this side of the can?
Positive.
Does that make sense then why the can rolls towards the balloon? Then as it rolls, the negative charges that were on this side, as it rolls to the balloon, what are they going to do now? They're going to go to the back side of the can again, making this side positive. So it's just going to continue to roll towards the balloon. I'm constantly moving electrons to the back side of the can. Did you all eat your breakfast today? You got your vitamins and your proteins and all that? I mean, you understand this, right? Makes sense, right? Okay. About ready to show you something. Hopefully this will make sense to you. Look at this. Now I'm going to actually do this when you guys are here on Monday. This is a cool thing, except I'm going to do it with you. We're going to ask a volunteer to do it, but I want to show you something first. So let me take that off. All right. So what is this thing? This thing is called a Van de Graaff generator. Okay. And it has an aluminum dome. Now go to that triboelectric sequence chart. It has an aluminum dome. Now, if you look right here, in this column, in this plastic column, I feel like Vanna White. In this plastic column, there are two huge, thick rubber bands, about that thick, that go like this. You're going to go up and then down, up and then down when I turn the switch on. Okay? When I turn that switch on, these rubber bands just go up and down, up and down. Now, that's rubber. This is aluminum. Now, I want you to look inside this thing. I don't know if you can see it, but inside, there are these little metal teeth right here. Metal teeth. Let's see if I can see it. You can maybe see them better that way. All right, there's these little metal teeth. When I set this on top of this column, a certain way, the metal teeth are, if this is the rubber band, the metal teeth are sitting on top of the rubber. So as the rubber goes around, the metal teeth are scraping the rubber band. So we have aluminum scraping rubber. Aluminum scraping rubber. So electrons are getting stripped off of one thing and put on the other. Looking at that chart, you should know what's being positive and what's being negative. We're good so far? Now watch this. Here I've got 3 aluminum pie pans. They're not attached to each other. They're just going to lay on top of each other, and I'm just going to lay them on top of the dome. Now I'm going to turn this on. This generates 50,000 volts of electricity. 50,000 volts. Do you know how much voltage comes out of your wall? You know, when you plug things into the outlet in your wall, you know how much voltage comes out of that? 110 to about 110 to 120. Only 110 to 120 volts. This is 50,000. Okay? Now, again, these pie pans are just sitting here. I'm going to turn this on, watch what happens, and I want you to think and figure out why it happened the way you saw it. Here we go. 1, 2, you gotta look quickly. 1, 2, 3. I'll do it again. Okay, once again. Aluminum pie pans, nothing special about them, putting them on top. Here, let's just do one. Let's just do one. One pie pan. Ready? Here we go. Watch. And there's no fan. There's no fan. There's nothing blowing on them. Why do they do what they do? Think about it. Who has an answer? Anybody? All right, I'll try to help you along. What charge does this aluminum dome? What charge does this aluminum dome have? This is aluminum and there's rubber. What charge will the aluminum dome have?
Positive.
Positive charge. Good, because aluminum and the chart is above rubber. All right, so if this is positive, that means all the electrons that this dome has and anything that's a part of it, all those electrons go to the rubber bands. So this all becomes positively charged, doesn't it? What happens if you have several things that are the same charge? What do they want to do if they're the same charge?
Repel.
Does it make sense why, when I turn this on, these all repel and get kicked off of each other as well as the aluminum dome? That wasn't hard, was it? Does that make sense to everybody? Huh? Yeah. All right, what about this stuff? You ready for this? Now, this is the one where I'm going to use one of you guys as a volunteer. And we're going to do this. I'll do it first for you when you're here on Monday, but watch this. So I'm going to turn this on, watch the green wig. So I've got a green wig sitting on top of the dome, just like these pie pans are on there, but this is heavier. All right, but watch what happens. You ready? Here we go. 1, 2, 3. Pretty cool, huh? Now, watch what happens when I touch the dome with this metal rod. So, who can explain what you saw here? Think in terms of the pie pans. I got one person that knows. Let's go with Morgan Childress. Morgan Childress, why do you think you saw all the hairs of this wig separate out? Can't hear you.
Sorry, I was on mute. Static electricity.
Okay, but why stick out? What was making them stick out, Morgan? What charge is the dome?
Positive.
Okay, yeah, we said that several times, and you should be able to understand why it's positive if I tell you this is aluminum and this is rubber.
Because aluminum's higher on the chart.
Boom, okay, so this is positive. And so when I put the wig on top of the dome, it's part of the dome.
Mm-hmm.
So now the wig is going to be what?
Positive.
Positive. Means all the electrons in the wig have been given to the rubber bands. So every hair on this wig is positively charged. So if you have two hairs that are next to each other that are both the same charge, what will those hairs
separate?
Yeah, and that's why you see it all stick up. Does that make sense?
Mm-hmm.
Now here's what's cool. On Monday, I'm going to get one of you yahoos to come in here. You're going to stand on a stool. You're actually going to put your hand on the dome, and we're going to have you do it. I'm going to send 50,000 volts through one of you. You're going to have your hand on the dome, and you're going to be standing here. What should we see?
Your hair stand up.
We should see that person's hair stand up, just like this wig. Hopefully. But I'll tell you what, I might do it first for you. I might put my hand on here so you can see my hair stand up. Of course, we know I'm a little bit at a disadvantage, so I may put this on. Okay, but we should still see it. And then I'm going to get one of you guys to do it. Does that make sense? What we just said? 50,000 volts though, man. It's a lot of voltage. Okay, a lot of voltage. I know you're sitting there going, well, man, if I touch it, am I going to die? That's 50,000 volts. Coach, you just said that the outlets only give you 110. That's because voltage isn't necessarily harmful to you. There's other things in that. There's things called current. And current is what kills you. All right. So that was kind of cool. All right, now let's get back to Ben Franklin. Look at Ben Franklin here. All right, so Ben Franklin was kind of a reckless scientist, man. He did things back then that we would never think about doing now. We all know that Ben Franklin was the dude that was outside during a storm flying a kite, right? With lightning all over the place. And he was flying a kite with a metal chain on it. Let's see this picture. So I don't know if you can see this, but here's his kite. Here's lightning right here. And this little thing that he has in his hand, that is actually a wire. So he's flying a metallic kite with a metallic wire in the sky during a lightning storm. We all know that's the dumbest thing to do, right? We know that. But you know why we know that? Because he did it. It always takes somebody to do something for us to know, hey, we can or we cannot do that. But he was trying to figure out the effects of electricity. And he knew that lightning had electricity. And the only way you could get lightning's electricity is to give it a pathway to get to you. And that's what he was doing with the kite and the wire. But we know today you would never go out in a lightning storm and hold a metal golf club up at very high. You know, we know we just don't do that. But that's essentially what he was doing. All right. So we're going to talk a little bit more about lightning, but I want you to look at this picture here. Benjamin Franklin designed the first practical and safe lightning rod, which would attract electricity and channel it to the ground. Here you have the roof of a building, and the roof is made of wood. When lightning strikes, okay, it wants to take the shortest pathway to the earth. So if the building is in an open field, the building's part of the field. But because the building's above the field and is part of the field, that would be the shortest pathway for lightning to get to the earth by striking the building. So what Franklin designed was something called a lightning rod, which is a sharp, pointed tip piece of metal with a wire that comes from it and runs down along the side of the house and then down into the earth. Okay? Now this wire is insulated. It's plastic all around it. So the wire is not actually touching, the metallic part of the wire is not actually touching the house. It's just, covered. So now what happens is when lightning strikes, it has a choice. It can either A, strike a metal lightning rod or strike the wood of the house. Well, metal is more of an attractor for electricity than wood is. And since the metal is part of the earth because of the wire, and the metal is above the roof because it's above it, lightning's going to strike that. And so lightning's then going to go down the wire, bypassing the house straight to the ground. So the house is totally protected. Now, would you believe that this invention of his affected women's fashion? This invention of his affected women's fashion. Back in that day, he was doing all these experimentations with lightning and he was freaking people out. And he literally was freaking people out because of all the stuff he was figuring out about electricity. So people started to get scared about being outside when it storms and it's raining and there's lightning. So what did women do? So what we started to see was women's fashion changed. If you look at this picture of these, there's a woman here, there's a woman here. They're wearing these hats. And if you look, there's even one here, and you can kind of see it. If you look, you can see at the top of the hat, do you see the metal chain or the metal wire? It's coming, it's right here. It's coming off the hat, and it's running down the backside of the woman all the way to the ground. Do you all see that? What the women were thinking was that if a lightning rod can protect a house, maybe if I run a wire from my hat down to the ground, if I'm walking outside and lightning strikes, it's going to strike the wire and not me and totally bypass me. That's the dumbest thing you can think of. Okay, for several reasons. All right. First off, the wire is not insulated on their hats. It's just a metal wire. So anything that strikes the wire is going to strike the body. Okay. Secondly, do you really want to attract lightning to your head? No. All right. Thirdly, why even walk outside during a storm anyway? But that was the fashion. That was the fashion back in the day. Hats were sold with metal wires on them for this very reason. Okay. Kind of interesting. All right, let's talk about how lightning is produced. All right, we've already learned of two ways of charging objects, and both these methods are used in the formation of lightning: friction and induction. So let's start by talking about what a cloud is. You all know that a cloud is nothing but wet dust. Up in the air, you have a bunch of dust particles that water vapor has collected on top of, and when it does that, you see what's called a cloud. The white stuff you see is literally water vapor, okay? Sitting on dust particles. Well, in a storm, these dust particles get all mixed up. They all kind of go together and they start rubbing against each other. There's the friction. There's the friction. And so as the dust particles get rubbed against each other, charge is created. The dust particles strip electrons off of other particles and deposit them onto the particles that are rubbing against them. So you end up getting a cloud with a negative charge right there in the picture. Now, when you bring this charged negative cloud near the ground, I want you to think of the cloud as the balloon, and I want you to think of the ground as the wall. Now, you remember when I bring a charged balloon near a wall, think about what happens. You see, here we have the earth, and the earth is neutral until you have a charged cloud near it. If this is negative, then what would all the electrons that are sitting on the surface of the earth, what would they all do when the cloud's near the earth? What would the electrons in the earth do if you have a negatively charged cloud near the earth?
They move to the more down in the ground.
Yep, they all go down to the bottom. So what does the surface of the earth become?
Positive.
Right, so we have a positively charged earth due to induction. So friction created the negative cloud, and induction now creates a positively charged surface. Well, ladies, this is what's going to happen. There are so many negative charges in this cloud. They have so much charge. There is a huge, huge attraction between the negative electrons and the positive earth that they jump down to the earth. They literally leave the cloud, move through the air into the earth. And when they do that, that's what you see as the light, are these electrons that jump from the cloud down to the ground. That's lightning. Now, you ready for something that you never have probably heard of? Lightning can strike from the ground up. Lightning doesn't always have to come from the cloud down. It can come from the ground up, because sometimes you get a cloud that's positively charged. And so all the electrons in the earth will jump up to the cloud, and you'll have lightning going that way. But both cases are created because of friction and then induction. All right? Everybody good with that? You know, the thunder you hear is the large expansion of the air that gets so hot from the lightning the air expands and slams into the colder air outside. And so when the hot air slams into the cold air, that's the sound you hear. So you see the light first, then you hear the sound, because sound travels a lot slower than light. Remember, light travels at 3 times 10 to the 6 meters per second. Sound is way slower than that. Okay? So that's lightning. All right, let's go to the next PowerPoint. So if you go back, find the one. Find the one that, let's see. Let me get out of this. Okay. Let me get out of this one. Okay, let's share. It should be called Coulomb's Law. I want you to find that one. It's called Coulomb's Law. And it looks like this. Okay. Oops, not that. Okay. All right. I'm only going to do a few slides here and then we're done. Okay. All right. So if I take this and charge it and this and charge it and bring them near each other, we know there's going to be attraction and repulsion, correct? So there's a force that exists between these two. Coulomb's law is all about that force. Coulomb's law is attempts to try to explain how much the force actually will be. Now remember, force is measured in what unit? What do we measure force in? What's the unit? It's named after a scientist.
Newtons.
Newtons, right. So remember what I told you? If you measure the force to be 1 Newton, what's that the same thing as?
An apple.
An apple that sits in your hand. If you take an apple and put it in your hand, that's how much 1 Newton of force would feel like. All right. So when we're calculating the force between 2 charged objects, if you get a force between these 2 charged objects that's like 20 Newtons, that's a pretty significant heavy amount of force, isn't it? Right? Okay, due to their electrical charge. But let me ask you something. Do you think that the charge of this balloon and the charge of this can is going to be a very high amount of, is going to create a very high amount of force? No. Remember, this only bent a small thin stream of water. If that stream of water was much thicker, it probably wouldn't have bent it because the water would have been way heavier, right, than the force of attraction that would have caused it to go to the balloon. So the forces you would calculate, when you get a force in newtons, you'll have a pretty good idea of how strong that force is. So you'll know how strong the electrical amounts are on both objects. Well, that's all Coulomb's law is doing. Okay. There is a huge amount of positive electric charge as well as a huge amount of negative charge present in the universe. All right. Fortunately, the vast majority of this electric charge is gathered together in atoms, which neutralizes the electric force of these particles. What does this mean? Ladies, what this means is everything in your room and everything in this room is neutrally charged to begin with, even though there are negative and positive charges in this room. There are tons of negative charge in your room and tons of positive charge in your room. And there's the same thing in your body. But your body is neutral. And that's because all the positive and negative charges that are in your body are mixed around and you have the same amount of each. You with me? But how powerful would the electric force be if we were able to separate all the charge that's in the universe? Well, let's, instead of separating the charge that's in the universe, let's separate the charge that's in a human body. So let's say that we take, for example, Meyer Davis. All right, Meyer, we're going to take you and we're going to take all of the positive charges that are in your atoms, so all the protons that are in your body right now, and we're going to separate them out of your body and put them on that side of the room. And then we're going to take all the negative charges that are in your body, Meyer, and separate them and put them on that side of the room. At this point, you no longer exist, Meyer. You're gone. Okay? You're gone. You're dead. You're gone. And all we have are all the protons that made you up and all the negative electrons that made you up. You with me? So the question now is, the question that's in the blue box is, how strong is the electrical force that would exist between all the protons and electrons that are in a human body once we separate them? Well, we have to assume a couple of things. First, on average, there's about 10 to the 28th electrons in the human body, and there's about 10 to the 28th protons in the human body. Notice the two numbers are the same. And that's because you're neutral. Okay? So if I took out all her electrons, Meyer's electrons, and all Meyer's protons, there's about 10 to the 28th over here and 10 to the 28th protons over there. So the question is, how strong is the attractive force going to be? Do we think it's going to be like between this can and this balloon? You know, where it's going to be a small number, all right, of force, or do we think it's going to be huge? Well, there's 10 to the 28th electrons. There's 10 to the 28th protons. They're separated by 10 meters. 10 meters is about the length of the width of this room. All right. When we do this and we separate them out, the attractive force that will exist is 10 to the 23rd tons. Guys, you know how much your car weighs? Your car weighs just 1 or 2 tons. If I put one car on top of you, would that be a huge amount of force? But that's just 1 ton. The amount of force that exists between all the electrons and protons in one person's single body is 10 to the 23rd tons.
Wow.
Yeah, wow is right. That is a huge amount of force. This is equal to 100,000 times the gravitational force between the Earth and the moon. So Meyer, you got a ton of electrical force in your body right now that you don't even know is there, because all your protons and electrons are all mixed up, creating a neutral kind of situation. But if we separate them out, that's the force you get. Pretty interesting, isn't it? Okay. Now, here are some basic ideas in electricity that we've already looked at. First, ions. Ions, we know, are charged atoms of an element. An example of that would be like sodium chloride. The positive ion, in this case, the sodium, is the electron loser, and the negative ion, like the chlorine, is the electron gainer. So the chlorine took the electron from the sodium. Okay, so chlorine becomes negative, sodium becomes positive. They go together because of the ionic bond. We also learned that the electron is 1,836 times smaller than the proton. But in spite of this size difference, the electron has the same electric force as the proton. So even though the electron is almost 2,000 times smaller in mass and in size, it has the exact same amount of force that a proton could have. That's kind of interesting. We would have thought that a tiny little electron would have a tiny electrical force. No, it has the exact same amount of force as a proton. And here's something new. This is the third way you charge an object. Another way that electricity can be transferred is through what's contact, known as conduction. Ladies, the word conduction comes from contact. And what conduction is if a charged object touches. See, that's the difference between conduction and induction. Induction, you bring a charged object near one. Conduction, you actually touch the object to the neutral one. Then some of the excess charge moves from the charged object to the neutral one, making the neutral one now charged. So if I go back to this balloon and I charge it up on my sweater, all right, negatively charged, bring it near the wall and touch it to the wall is now charged, because when I take this away, just a little bit of the negative charge that's on the balloon is now in the wall. So the wall is now negatively charged because of the contact. Before, when I brought the balloon near the wall, the wall was positively charged due to induction. So you have to be able to identify the difference between friction, induction, and conduction if I give you several different examples of scenarios of things that are getting charged. So make sure you can do that. Okay, I'm going to stop here